So, back in February of this year, I was in Taiwan. My son got a prize to go visit Taiwan, and I went along, and they treated us very nicely. And at some point of time, I went to Confucius Temple, Taipei, basically. Taipei is a beautiful city, lovely, lovely city. Anybody from Taipei? Okay, it's a great city. So anyway, Taipei is a beautiful city. I was walking around, and then I went to this place, which is the Confucius Temple. Confucius, I know all the Chinese know it at least, and the rest of you who don't know it, you need to figure out who he is. Anyway, then it turns out, that's of course the temple. And then as I was walking around outside in the courtyard before getting in, I picked up this little thing, brochure on the Confucius temple, and in particular Confucius, is full of wisdom, right? That's what we talk about, Confucian wisdom. And so essentially this brochure was going to, talk about the Confucian learning and wisdom and so on. So I picked it up and I was looking at it, and I realized, of course, they talked about various arts that children used to be taught in Zhou Dynasty. Zhou Dynasty, I don't quite know when it was, but I'm pretty sure it was way, way back then, okay? And they used to be taught these 6 arts, and one art, so these are the 6 arts of Confucius. You keep reading it, you realize that they had, one was music, one was archery, one was chariot riding, useful stuff, and then I realized that they also had calligraphy and computation. These people from East, like they're all into computer science way before computers were invented. Which is surprising. It was good, but I kept paying more attention, exactly what were they learning in computer science, so that I can come and give you the wisdom they had, right? Okay, you probably can't read this stuff, so I blew it up for you, and so that's the first part. So this is the part, and this is the first part. If you read it, you realize that they were learning latent Dirichlet allocation. Not just latent Dirichlet allocation. They were learning complex latent Dirichlet allocation. When was this? It was not in 2000. It was by elementary school students during Zhou Dynasty. Now you know that Obama won and he wants all of you guys to be competitive and keep up with the others, right? These guys apparently know latent Dirichlet allocation in elementary school. So I thought at least graduate school you should know what it is. Otherwise you're stuck. All your jobs are taken by Zhou Dynasty elementary school kids. What's interesting, of course, is latent Dirichlet allocation, which was obviously known to elementary school students during Zhou Dynasty, was reinvented, in US by this guy called Michael Jordan and David Bly. Clearly they must have copied it from somewhere. So I sent them a mail pointing this out. And that, obviously you must have copied it from the children's elementary book. And I think Michael Jordan was trying to make some joke out of it, but really, I'm pretty sure he copied it. Anyway, there is a reason to understand latent Dirichlet allocation. That's my point. Okay, so if you ever leave US, your jobs are all going to be taken by these Zhou Dynasty elementary school kids, if you don't know it. Okay, so that's why we're going to do LDA. The agenda for the class, of course, is, as I mentioned, I want to actually understand the LDA idea. It comes from 2 different directions. One is from topic modeling, which is just a useful application in many, many things. And also from graphical models, okay, which is basically Bayes nets and so on. And since I know that people who did 471 with me definitely know the stuff that I expect them, I would be assuming here. It wasn't quite clear to me how many people know enough about Bayes networks. So I am going to I decided that I'll go a fast introduction to Bayes networks, which my sort of hopeful way, I'm thinking I'll be done in today's class, but if there's a little left, then we'll do it We come back on Tuesday. Notice, of course, that what I'm trying to cover, I covered in the 471 in about 8 lectures. Okay, but then the videos for that are completely available. So if you don't know this stuff and you need more information on this, just look at the 471 videos or look at anybody else's. Anybody else's yes. So if you go to 471, there's a whole bunch of lectures on so starting here, handling uncertainty, and it's like a very more gentler introduction, and then a whole bunch of lectures on just the inference part, and then a bunch of lectures on learning the Bayes networks part. Okay, so what I did there in about 8 lectures, I'm going to try and do in one here. Again, as I said, it's better than, if you don't know anything about Bayes networks, this is better. At least you will know what you need to understand. And in particular, I'm only going to focus on the things that you need to understand at a bare minimum to understand latent intelligent allocation, which is the more advanced topic. So that's what I am going to do. And as I said, if you have questions, further questions, look at the lectures or read the textbook, and you can do it also on an as-needed basis. Okay. So that's the slope-of introduction now. Okay. So basically, graphical models are used to compactly represent joint probability distributions. Okay, so the simplest idea is to think in terms of, again, Boolean variables. We'll start with them. Okay, so if you have n Boolean variables and they're all random variables, then you essentially will need the joint distribution over these Boolean variables tells you, suppose the n Boolean, if you have 3 Boolean variables A, B, C, the joint distribution tells you what's the probability that A, B, and C are true, what's the probability that A, B are true and C is false, what's the probability that A and B and A is true, B is not true, C is not true, and it gives the probabilities for each of these possible words. Okay, since obviously there are going to be here 2 power 3 words, so there are in general 2 power n different words. Okay, what we are saying is each of these words have different probabilities and they all sum to 1. Okay, that's the joint distribution. Now normally representing a joint distribution for n variables will require 2 power n numbers. In fact, it will only require 2 power n minus 1 numbers, strictly speaking. Okay, minus is of course outside of the 2 power n, right? Because the rest will be just added up. Okay, but 2 power n minus 1 is way too many variables, way too many numbers. So in fact, one of the big things to understand about probabilistic reasoning is not how to crunch the numbers, but how to get the numbers to begin with. Where do you get these many numbers? Now, of course, you can ask your friend, just make up some numbers and then I'll use them. Okay, so that ends up being the huge problem. How do I get 2 power n minus 1 numbers? Now it turns out that if the variables do have certain structure in terms of their probabilistic dependencies, okay, so I'll draw the same kind of a graph as before. So this is a graph now. This graph has no edges. If this is the way A, B, C are, you would be the happiest person on earth. Because then that means A and B and C are completely independent of each other. In which case, you just need one number for A, one number for B, one number for C. That's probability of A being true, probability of B being true, probability of C being true. Given that, you can compute any one of these entries because they're all independent. So instead of looking for 8 numbers, you can get by with just 3 numbers, which doesn't look like a huge thing normally, but if you have n equal to 10, instead of 10 power 24 numbers, you can get by with 10 numbers. If n is 100, then instead of 2 power 100 numbers, you get by with 100 numbers. Amazing. So you reduce the number of numbers needed. Now, of course, any world where everything is independent of everything is a really boring world. Okay, where basically the whole point is that somehow by working on some variable, you're affecting other variables. And if they're completely independent, yes, you would be done fast, but you won't be able to do anything useful. In fact, this reminds me of a very deep, at least pseudo-deep sounding quotation, saying that I read once, that if human brain is so simple that you can understand it, we would be so simple that we can't. Okay, and so something like that. So essentially, if you wish for completely independent distributions, then basically, first of all, they're not true mostly, and secondly, even if they were true, you don't want to live in such a world because you can't have any effect on the world. Okay, but however, this tells you what is the direction to go. The direction to go is look to see if there are independences between variables. If every variable is connected to every variable, if every variable is probabilistically connected to every variable, then in essence you will wind up needing 2 power n minus 1 numbers, and you shouldn't complain. On the other extreme, nothing is connected to anything, and so you will just need n numbers, and you should be happy. Okay, so this is ABC, here is another ABC. That's a complete graph. And in the case of complete graph, essentially everybody depends on everybody, and so you will need, 2 power, n minus 1 numbers. The idea is, can we talk about middle grounds where essentially the topology of the graph tells you what dependencies hold, and so by extension tells you what independencies hold. Okay, now for example, if you have 3 variables, weather, cavity, toothache, and catch, this is a dentist example. Okay, now presumably since weather has nothing to do with having cavities and having toothaches and having catches, weather is off on its different side. Okay, and I'm saying cavities cause toothaches, cavities cause also catch. You may not, and if you haven't seen this example before, you won't know what the heck catch means. Apparently, this is that thing that they put in your tooth, to see if it gets stuck or not. I mean, nice, sweetie thing. But anyway, so you're trying to figure out whether or not there are cavities in somebody's teeth. Okay, and you're trying to reason this out. And if they have toothache, maybe they have cavities. If they have, when you kind of hang around and kind of poke around their teeth, if the thing gets caught, then that might also mean they have cavities. Okay, so in essence, I'm looking at a graph like this. In particular here, I have directions. Okay, so this thing looks almost like a constraint graph, right? Except for the directions. Okay, so in fact, many of your insights from constraint graphs actually carry over to probabilistic models. In fact, in the chapter that I gave you from Dexter's book, she talks about this idea called bucket elimination algorithm and variable elimination algorithm. Those of you who did 471 know variable elimination algorithm is actually the first exact algorithm for dealing with inference and Bayes networks. And bucket elimination algorithm is something that Dexter developed for CSPs and just exported it to probabilistic reasoning. So at the level of graphical structures, there are lots of things that come forward. In fact, even the idea of induced bit, it turns out, is very much relevant. In fact, it winds up affecting how hard it is to do inference on probabilistic networks. If the induced bit is 1, it's easy, otherwise it's not. Okay, but we'll get to that soon enough. Okay, so this particular graphical model, this model is called Bayes network. Okay, it wasn't invented by Reverend Bayes. Okay, it was actually invented by this guy, Julia Pearl, and it was a big enough thing that he got Turing Award last year. Essentially for that. If you read this, you will wind up seeing it. Actually, it says there that focusing on conditional independences as an organizing principle for capturing structural aspects of probability distributions. That's part of the citation for which he got Turing Award. Okay, so of course, it's very important. I mean, obviously theoretically important, but also practically they are very useful ways to represent probabilistic distributions in a compact form. Okay? The assumption in this particular case is you have 4-node network. You would have normally needed 2 power 4 numbers. But the way I wrote this, I wind up needing much fewer numbers. How many numbers do I need? It turns out that all you need, so notice this did not say anything about probabilities, right? As it is given right now, yeah, as it is given right now, there are no probabilities here, okay? But this is the first structure of the network. Just like in constraint graphs, first you give the constraint graph, then you write what is the constraint on the graph. Right? Remember, you write x is connected to y, z is connected to x, and then you say not equal to, not equal to. That not equal to is the constraint. Similarly, you want to talk about the probabilistic constraints after you have provided the structural information. Okay? In particular, all I need is once I get a network topology like this, all I need to provide is a conditional distribution for each node given its parents. That's all I need to give. Conditional distribution for each node given its parents. Okay? So for weather, there are no parents. So all I need to give is P weather. Just one number. For cavity, there are no parents. No parents are in terms of directional sense. Cavity, there are no parents, so I just give P of C. And for toothache, there is one parent. So I need to give P toothache given C and P toothache given not C. Notice that I don't need to give you P not toothache given C because that plus that should add up to 1. Okay, similarly here I need to give you P catch given cavity and P catch given not cavity. So how many numbers did I give you? One number here, 1, 2, plus 2, 4, plus 2, 6. Instead of 16, I got by with 6. Okay? Now from these 6, I can magically reproduce all the 16 numbers. In fact, a way of understanding the semantics of graphical models, even though that's not the way you wind up doing, is that the graphical model compactly represents the entire joint distribution. And if you know the entire joint distribution, you can answer any probabilistic way. Okay, so if you lost all other ideas, then what you can do is go from here to the 16 numbers. And once you know the 16 numbers, you can answer any probabilistic way. Okay, and much of the efficient algorithms for Bayes networks are all about how to avoid actually enumerating the entire joint distribution and just answer your query without having to enumerate the entire joint distribution. But that we'll get to that. Yeah. Okay. Okay. So actually, I should put this. This is the. But anyway. So here is another example. This is the one that actually the textbook talks about. It's the burglar earthquake alarm. John calls, Mary calls. And in fact, you can think of this as this is in terms of Los Angeles, where there are earthquakes possible, and Pearl actually made up this example long back. And so the theory here is you may have a burglary at your home, or you may have an earthquake at your home. Either one of them can set up the alarm. If the alarm goes off, either John might call you in the office or Mary might call you in the office. Or both might call you in the office. Now, you can talk about logical. You can think of this as just a direct logical graph, in which case, if burglary occurs, then alarm will go off. If earthquake occurs, then alarm will go off. And if alarm goes off, John will call. If alarm goes off, Mary will call. But, normal worlds, people have other things to do, so they may not actually call. So they're only probabilistically likely to call. And normal worlds, burglary may not actually set off the alarm. If the burglar is particularly smart, they will probably know a way of not letting the alarm go off. And the same thing, earthquake, if it is mild earthquake, may not let the alarm go off. Okay, so this basically is the distribution. This is the causal model for this particular example here. By the way, even though we look at causal model, it turns out that Bayes networks are really not causal. It turns out that it is useful to write them in the causal direction, if you know the causal direction. In many words, you don't know the causal direction. Okay? And in fact, all Bayes networks care about is if you give a particular configuration of the network, you must give the conditional probabilities for every node given its parents in that particular configuration. And there is a whole entire discussion in 471 as well as in the text about how if you know the causal direction and if you write the network in the causal direction, then you are likely to have to assess probabilities that are much more robust. They don't change as often. So that's why people tend to write Bayes networks in the causal direction. But causal direction is not required for Bayes networks. In fact, there is no causality required in the graphical models. Okay. So here anyway, we wrote this in sort of the causal direction according to our understanding of the domain. And so what would you need to give? You need to give a prior distribution for B, prior distribution for E, a distribution of A given B and E, a distribution of J given A, a distribution of M given A. If you do that, you will be done. Now, if I didn't do that, normally I would have required 32 numbers because there are 5 Boolean variables. If I do this, then essentially I will have this network. I just made up the numbers in this case. Okay, so the network I have said is the burglary probability is 0.001, earthquake probability is 0.002, alarm probability must be given with respect to burglary and earthquake. And so this is the conditional probability table, and this is how it looks. Okay, and then similarly, John calling given alarm probability is given by this little table, and Mary calling given alarm is given by this little table. Those are the conditional probability tables. Now notice, by the way, we'll get to it later, but the conditional probability has to be provided. Okay, but it doesn't have to be provided as a tabular form. If you can't do anything else, we'll always write it as a tabular form. But we sometimes will, little later we'll look for more compact ways of writing this itself. So a way of thinking about this is these tables, if you think of this as the constraint graph, and so the constraint graph still exists here, the tables correspond to the constraints in the CSV. And remember, we talked about the fact that constraints can be represented extensionally or like opaque pieces of code. They can be written, when you represent it extensionally, you can write it either as just legal assignments or illegal assignments. And if you can write opaque pieces of code, you can write it as x plus y less than or equal to z. And then somebody just checks, at the time of, the search, whether x plus y is actually less than or equal to z. And writing x plus y is less than or equal to z is a much smaller representation of the constraint than writing all the legal or illegal assignments. But at the bottom of it all, writing illegal or legal assignments is the first principles approach. You see what I'm saying? So we will understand Bayes networks at least at the level of how to deal with extensional conditional probability tables. That's what you need to understand at least. Okay. So anyway, that's that. And what's interesting about this network configuration is, as I said, if I give you the network, you should be able to reconstruct the joint distribution. Okay. Now, what does joint distribution have? It has entries of the form burglary, earthquake, not alarm, John calls, Mary calls. Or burglary, not earthquake, not alarm, John calls, not Mary calls. There are 32 of these. For each one of these possibilities, I need an exact number. The exact probability that would be true given this network. Okay? That's where the whole notion of conditional independencies winds up coming into picture, and in particular, it turns out that there is chain rule that can always be used, it just always holds. So if you have, you can always write PAB as PA given B times B, or PE given A times PA. Right? That's basically just part of definition of joint distributions, joint probabilities. Okay, these are true for single number, they're also true for entire distributions. Now, in fact, actually, this is where what you know as Bayes rule comes from. Right? because P A given B times PB is equal to PB given A times PA. So Bayes' rule says that you can write PB given A to be P A given B times PB by PA. That's Bayes' rule. Just comes directly from, first principles. In fact, the interesting thing is Bayes is not famous for this particular rule, although most of you know him for this reason. Bayes is famous for a completely different reason from probabilistic reasoning point of view. Bayes basically said probabilities don't have to be frequencies. So in statistics, there are two completely different camps. One camp says a probability is a asymptotic frequency. So if you can't actually set up an experiment which will measure that frequency, then it's not a probability. Okay, that's the frequentist statistics. And then Bayesians, and starting from Bayes' rule, basically take the view that you can give any numbers. You can make up numbers. So for example, a way of telling a frequentist from Bayesian is if you ask, what's the probability that let's say Stalin was drinking tea on October 3rd, 1947 at 2 p.m. in the afternoon. What's the probability? And you would say, how the heck do I know? I don't know how to set up this experiment. Okay, how can I give the probability? If you say that, then you are a frequentist. If on the other hand you say, I'll just give it a number. Okay, and they'll say, I think it's like, well, it's evening, right? And Russians don't really drink that much tea, so I'll just make it 0.001. Then you're a Bayesian. You made up a number. Okay, that's the bigger reason why actually Bayesian statistics versus frequentist statistics differ. But for our point here, of course, we went with chain rule, and the chain rule actually leads to Bayes' rule. But chain rule also gives you one more thing, which is the generalization of chain rule is if you have PABC, you can write it as PA given BC times PBC, which itself can be written as PB given C times BC. This is just probabilities. This is just definition of conditional probabilities and conjective joint probabilities. Now, the reason this is important is if I were to write, so notice that I need to write probability of burglary, earthquake, alarm, John calls, Mary calls. Okay? So I will write this here. Probability, burglary, earthquake, alarm, John calls, Mary calls. PBEAJM. Okay? Right? I can write this using just chain rule, right? As PM given BEAJ times PBEAJ, which I will write this as PJ given BEA times PBEA, which then I will write as P A given BE, you're catching on, times BBE, which I will write as PB given E times BE. Okay? So, I can get you this number. This is what the number you want, right? I can get you this number. If you can give me this number, this number, this number, this number, this number. That's it. If you give me those 5 numbers, I multiply them, I'll give you this number. What I would like to hope is somehow those numbers are present in the network. Okay? So, let's see. PE is certainly present. I know the PE. So this for sure is 0.02. Okay? Now PB given E, what is that? PB given E, I don't know what is PB given E. There is no PB given E here, I only have PB. this is where the semantics of Bayes networks come. Remember we talked about networks in terms of independencies? Okay, even though they show the dependencies, what we are most interested in is independencies. It's the independency which tells you that PA given B is just the same as PA. That's when A and B are independent. Do you understand what I'm saying? So, I would basically say PB given E, so I basically want to say B is independent of E. If I can say that, then PB given E is the same as P of B, which I know. And that would be just 0.001. Okay? But then I would need A given BE, which actually is nicely present there. Okay? And then I get J given BEA. Once again, I have J given A. I don't have J given BEA. Once again, I would like to say J given A is the same, J given BEA is the same as J given A. If I can say that, I'm done. I will say it. And I will say that what I just said now is the same as what I said earlier. In particular, the general rule is a node is independent of all its non-descendants given its immediate parents. That is a conditional independence that holds in this graphical model. Okay, that's actually the theory of networks. Okay, so Pj given ABE is the same as Pg given A. In some sense, alarm sort of says the only way John gets affected by burglary and earthquake, given this network, is through alarm. If you know the effect of alarm on John calling, then you don't need to know the effect of burglary and earthquake. To the extent they have any effect on this, they have it only through alarm. That's what this network is telling us. Actually, if those of you who already heard of Bayes networks, it would be nice to keep thinking in the background about how does this connect to CSPs. You can have constraints directly from burglary to John calls, or just burglary to alarm to John calls, and the consistency checks will change based on where the constraints are. That's a useful exercise to do instead of falling asleep. Okay. Anyway, so basically the global semantics is that the full joint distribution is defined in terms of just the numbers that are available in the conditional probability tables. And the way you define it essentially is that the variables are independent. Any node is independent of its non-descendants given its immediate parents. And so because of which, so first I'll do the first step, which is just writing using chain rule, which just holds always. Chain rule holds irrespective of the network. The only thing is that I can do the chain rule in any order I please, and it will be correct. So as I said, PAB can be written as PA given B times PB, or PB given A times PA. I get to choose which one. And I'm going to choose the order that would be most useful for me given this network. Because obviously if I write it upside, bottom up in this directed network, then I will get things, then I can just read off the numbers from the CPTs. That's what basically graphical models are telling us, the Bayes networks are telling us. Okay, so this is what I wrote here, J given M A not B. So in fact, I'm computing a specific probability here. J, M, A, not B, not E is written using chain rule this way. Then this becomes just this becomes just this remains the same, this becomes just that based on the conditional probability, conditional independences. And once they become that, I can read out those numbers. Can I multiply those numbers? I get in this case 0.000628. And that's the joint probability distribution. For joint probability distribution entry for this particular probability. And there are 32 other such ones, and you can compute all of them. Right? As far as you know, as far as you are concerned, I told you a way of writing, if anybody gives their compact distribution as a graphical model, compact distribution as a graphical model, then you know how to compute the joint distribution. And once you know how to compute the joint distribution, you can compute anything. from there. Okay? That's the basic idea of graphical models. Okay. Now, you can actually go a lot more deeper into the theory of base networks. The theory of graphical models is all about which exact conditional independences hold given a particular network configuration. All I really needed, all I'll ever need while computing a full joint distribution entry is, this immediate parents. Given immediate parents, I'm independent of all my ancestors. Because if I write everything in the bottom-up order, that's the only kind of questions I'll ask. But in general, I might just ask, okay, suppose I give you burglary, is burglary independent of earthquake? I can ask you that question. And you would say yes. Then I'll say, what if I give you alarm? If I tell you alarm is going off, is burglary independent of earthquake? It's not. And those of you who haven't thought about it, it's surprising. Okay, but it's not surprising when you realize the plausible reasoning involved here. Because once I know alarm is gone off, and I know that burglary occurred, then I don't need earthquake also to occur. It reduces my need for earthquake to occur to explain alarm. Do you understand what I'm saying? The alarm can be explained away by burglary, so the belief in earthquake reduces. That's one way of understanding that. In general, essentially, burglary might be independent of earthquake while knowing nothing, but the moment you get some evidence, they become dependent. This is the tricky thing that happens in probabilistic reasoning. As you learn more, things get connected. Okay, and so I should be able to answer queries generally of the form, given a set of x variables and a set of y variables, is the set of x variables independent of y variables if I give you evidence on z variables? If I can answer this question for any subset x, y, z of the original set of variables, then basically I know how to answer all the conditional independence assertions. Now it turns out you can live in Bayes networks without understanding how to answer that question. However, if you're interested in the theory, that's what you need to understand. How do you get these conditional independence assertions? And the minimum that you want to understand is two ideas of conditional independences. One is x is independent of all its non-descendants given its immediate parents. Okay, what that means is, so you are an x, if I were to give you u and m, which are the immediate parents of x, then x would be independent of all its non-descendants. This is a descendant, so it won't be independent of this, but it would be independent of everybody upstream, given just the parents. Do you see what I'm saying? So it's like a little bit of a blanket, but it's a partial blanket over x. Okay? If you were to give the immediate parents, then the probabilistic influence of all your non-descendants, which are sort of ancestors and siblings, is shielded by the parents. So somehow your parents shield you from your siblings, which they do. If you're kids, they're always stopping them from fighting. And also they shield you from your ancestors. But they don't shield you from your kids. Okay? That's one set. This rule will hold if you understand, if you have a sound and complete procedure for doing this will just be a special case of that. Everything that is independent by this rule is still independent, but there are more things that are independent that you won't catch with this. Because in particular, you won't be able to talk about, is x independent of somebody here, given, let's say, y1 and yn. To do that, you want to understand an additional notion, which is the Markov blanket. It's a full blanket. Okay? If you are given the Markov blanket of a node, then it is independent of everybody else when it's securely inside this blanket. The way you provide the blanket is you provide the values for all the variables in the blanket. Now what's a blanket? Blanket certainly includes the parents, it includes the children, and it includes the other parents of the children. Sort of a, what is this, the modern family kind of a thing. Okay, it includes, your parents and your children and your children's other parents. Okay, and that's your Markov blanket. And once I give you the Markov blanket, then X is shielded from everything else around it. I didn't even show what is there outside because I don't care. If I happen to know the values of these, then X is independent. If I know these variables as evidence, then X is independent of the values of all the other variables. That's the Markov blanket. Okay? So that's useful. In a minute, we will talk about how to use this in actually doing inference techniques, an inference technique for Bayes networks. In general, conditional independence assertions are not needed by people who just use Bayes networks as a toolbox. They don't need to understand it. Okay? But they are needed for those people who design algorithms for doing inference on Bayes networks. But I'm hoping some of you might be in that. So then you need to understand conditional independence assertions. Because the way you show that your algorithm is sound or complete is by using the conditional independence assertions. But if you're just calling the toolbox, it will do the thing. Why do you care? Okay? Questions? Okay, so that's about Bayes network representation and the conditional independence assertions of, that are inherent in Bayes networks. Okay? Now what I want to talk a little bit more about is, if I give you a network like this, obviously instead of 32 numbers, I only have right now 1, 2, 6, 8, 10 numbers instead of 32. That's a big improvement. Okay? In general, instead of being 2 power n numbers, you only require of the order of 2 power d numbers, where d is the maximum number of parents any given node has. You see what I'm saying? And that's a max, that would wind up basically dominating. That would wind up dominating the number of variables, the number of probabilities that you would need to provide. Okay, now as we are going through this discussion till now, the question is, who gave me this probability distribution representation? Till now, you more or less assume I just wrote it down for you. I wrote both the topology and the numbers. When we go to the learning part of this lecture, we'll talk about how to learn those things just from data. You see what I'm saying? Okay. So for now, even if I'm just writing it, even if I'm giving it to you, my life would be pretty damn hard if I have to give large number of numbers. I would be happy that I didn't have to give 32, I only have to give 10, but I would be even happier if I only have to give like a few less than 10, much less than 10. Okay? So to do that, what you do then is you use a different idea that you already know, for writing distributions in a compact form. Do any of you know distributions written in compact form?
Probability distribution model.
Any probability distribution models. Most of you certainly know normal distribution. So you can actually have a conditional normal distribution. Suppose you have a normal distribution. Okay, so suppose I want to say Bernoulli is a real valued variable that is normally distributed. Suppose I wrote it as a table. How big will the table be? What? No, table, tabular representation. Infinitely large. So you are so happy that you figured out a simple way of representing these infinite number of numbers as parameters of the normal distribution. These are basically what are called parameterized distributions. So think of conditional probability tables, the CPTs, as like the lowest level. If you have no better idea, this is what you would have to wind up writing down. If you can see some kind of a pattern in this, then you can probably write like a closed form parameterized distribution. Okay, much of what statistics has been famous for is, if you take any introductory statistics courses, you probably don't think in terms of writing things in the tabular form at all. You say, oh, we use normal distribution this time, we use, Bernoulli distribution this other time, we use multinomial distribution this other time. So they just tell you when to use which distributions. But if you have a situation and it doesn't fit any of those distributions, then you're on your own. Do you see what I'm saying? Okay? So we basically are going the opposite way. We are saying, you are trying to represent some arbitrary probability distribution. And in the discrete case, at least you can understand how you can make it smaller by just knowing the conditional independences. And you have this other idea that you know of making distributions smaller. You can write them as parametric ways. So in the discrete case, does anybody know parametric distributions? You know continuous distributions. Normal is a continuous distribution, right? The entire exponential family for continuous distribution, continuous variables are there. For discrete, Poisson is, for example, a discrete distribution. Geometric distribution is a discrete distribution. Okay, binomial is a discrete distribution. But actually this is basically what we are giving for the binomial distribution in this case. The table basically is assuming it's a binomial distribution. It's assuming it's a multinomial distribution. By the way, although I started by saying all variables are Boolean, it's very easy to actually make variables be multi-value. No big deal. No, if the alarm can have values 1, 2, 3, then you just have a bigger table. And similarly, actually, it is also possible to use continuous variables inside the Bayes networks. That is something that we haven't talked about in the 471 lectures, but we will actually need to use it for LDA because there are continuous variables in LDA model. So in general, in the most general case, the Bayes network might be a set of either discrete or continuous variables connected by the probabilistic dependencies. And you write it that way because you don't have any simple off-the-shelf parametric distribution that you can fit to the data. And this will basically be the right way to fit that data. So it will be basically combine these various parametric distributions as well as extensional distributions that are CPTs to give you the full joint distribution. Okay, so basically in this particular case what I'm saying is that to reduce the number of numbers that you still have to specify, one idea is if it's possible, rather than give the entire CPT, give parametric distribution. When you give a parametric distribution, do you lose anything? When you are agreeing to give a CPT, then any arbitrary relation between alarm and John calls can be captured in terms of a specific CPT. Okay, whereas if you decide to go with a specific parametric distribution, then you just hope that the true distribution that is connecting these two variables is close to some instance of this parametric distribution. When we say it's all normal distribution, we are just hoping that the true distribution is close enough to some parameter values of the normal distribution. So you do lose something in terms of, getting the real world aspects of the distribution. But what you gain is speed of reasoning. Because now you can specify the things faster and you can also reason with it faster. Okay, so CPTs can, I'll come back to the problem in a minute, but CPTs can still be quite hard to specify. If there are too many parents, so the solution is parameterize the CPTs. One simple idea, I'll come back to that or the previous one in a minute. One simple idea, even within CPTs, is this idea called noisy R distribution. Okay, the noisy R distribution says, suppose, basically so if you have cold and flu and malaria, these are your symptoms, okay, what's the probability that you will have a fever? That's what you're trying to capture. So fever is, in your network, fever has as its parents cold, flu and malaria. So to give the CPT, I need to give all these numbers, which will be 8 of them. What noisy R will say, essentially, is that the failure probabilities are all independent. That means the probability that cold doesn't cause fever is independent of the probability that flu doesn't cause fever. And my example, my best way of understanding this is think of you being shot by, you did something carelessly in the class or something, so I put you in front of a, firing squad, 15 people, and then they're all independently shooting at you, right? Now I'm trying to figure out probability that you would still survive, because I don't want to actually go to academic probation or something if you go away, right? So the point then I would say is that the probability that when this guy fires, you would still survive is independent of the probability that when this guy fires, you will still survive. Because they're all independently firing. In fact, they set it up such that way apparently. If you are into the politics of the firing squads, the way it is set up is nobody would know exactly whose bullet killed the poor guy, so that they won't have any guilt complex associated with it when they go home. Okay? So if you do that, then essentially all I would then need to do is to give 3 numbers in this case. So for example, here I give a number, probability when malaria is true, you still not have a fever is 0.1. When flu is true, you still not have a fever is 0.2. Okay? And similarly, when, what's the last one? This one, 0.6, yeah. When cold is true, you still not have a fever is 0.6. These 3 are the only numbers I will provide. Then the probability that when you have both flu and malaria, you still dodge the bullet of having the fever is basically multiplication of those 2 probabilities. You see what I'm saying? So I get that in this case 0.2 times 0.1, 0.02. And because I got a 0.02 here, this must be 0.98. So in essence, with these 3 numbers, I can fill up this column. And once I fill up this column, I can fill up this column. That's basically what noisy R distribution tells you. Okay? This way, instead of, even if the node has d parents, instead of requiring 2 power d numbers, I just require d numbers. Now, of course, when I decided to model the relation as a noisy R distribution, I put an extra bias. I'm saying that failures are independent. If that's not true in your domain, then you just made a wrong decision, representation decision. Okay. Other things you can do for conditional distribution. So, for example, here is a hybrid discrete continuous model, where this one is a Boolean model. Is there a subsidy or not? And how big is the harvest? And that defines how costly you want, how much cost you're going to charge, I guess a farmer. And then depending on your cost, people either will buy or not buy from you. You see what I'm saying? So that as a farmer, you set your cost based on the harvest, this year, and whether or not the government is still subsidizing. But then your cost then decides whether or not people are going to buy. So those are the variables. In this case, obviously, there are both continuous and discrete variables. Okay. So in particular, I am going to, let's say, the cost given harvest and subsidy. Right? That's basically, given this network, I need to provide a conditional distribution for cost given harvest and subsidy. Except cost is not a Boolean variable. So I need to give an actual continuous conditional distribution. Okay, if I write CPTs, I'm dead in the water right away, because if you have a continuous variable, then writing a CPT, you're dead. So you just have to do parameterized distributions. So if you come from the continuous world, which is what you did if you took any statistics course before, you would always only think in terms of parametric representations. But then what you might have forgotten in doing so is that if in fact the specific variables you are trying to, the dependency between the specific variables that you're trying to model, if it doesn't fit neatly into one of these parameterized distributions, then what happens? Then what happens is you get bad model. Okay? To the extent statistics is still around, there are enough reasonable models that you can fit. But graphical models are trying to increase the reach of elementary statistics, in essence, by providing arbitrary distributions and then providing them compact representations. Okay? So, so in this particular case, I would just provide a conditional normal distribution, a Gaussian distribution. So basically, probability that cost is C, given harvest and subsidy, is essentially a Gaussian distribution or the normal distribution for cost, which has the mean which depends on harvest level and the variance, which I guess what this is 80 times harvest, and subsidy equal to 2. So when subsidy is equal to 2, this is the case. That's the way I do it. Okay, where the mean for the conditional distribution is based on the harvest level. So that's what I did in this case. Okay, this is the way I could avoid writing a big, infinitely large conditional problem. Okay. I can also, in this case, cost to buys. That is a different kind of a distribution. Here, here it was discrete. So the harvest is continuous, subsidy is Boolean, and cost is continuous. So you have to provide a conditional probability distribution for cost given subsidy and harvest. But you also need to provide buys given cost. Buys is a Boolean. Cost is a continuous value. So you need some sort of a thresholding function. You need a distribution that looks like a threshold, and there are multiple such ones. For example, the probit distribution, which is essentially the integral of the normal distribution up to a point. Okay, and that basically can be used. Okay, or you could use the logistic distribution. Okay, both of them have the distributions look like that, which sort of look like essentially a nice threshold. Okay, again, here, this is the kind of thing that you will understand quite directly if you're coming from continuous statistics. Okay, because you always take something in your shelf and then see if you can fit it there. And so, if you're coming from there, notice that if you have subsidy, harvest, cost, and buys, what would have fit directly from your shelf? There is no single thing that would have fit directly from your shelf. So I'm actually able to model subsidy, harvest separately, and the connection between subsidy, harvest, and cost as a normal distribution, cost to buys as a logistic distribution. And I'm still able to reason with these things. And by the way, one of the interesting things is that it's actually very useful to understand this dichotomy between starting from CPTs versus starting from parameterized distributions. So for example, something like Kalman filters that some of you might know, I know at least a couple of you are from robotics and you will know. Kalman filters make sense only because you start with normal distribution in the beginning, which only requires 2 numbers, and as you continue computing posterior distributions, they still remain normal. And so you can still represent them with 2 numbers. When there is nonlinearity in the system, even if the first distribution is normal, the next distribution may not be normal. It might have multiple modes. And then as you go on and on, you will get multi-modal distribution, which will require a lot more numbers to represent. And that's basically, people consider that a bad thing, because you have too many numbers, you have to do a lot more reasoning. Okay? So anyway, so that's sort of a useful connection to make. Yes, sir.
So are we learning this model by the data?
Right now, I'm just setting these models. Okay, think about all of this right now as I'm giving it in. So until now, we are just we are basically acting as if somebody gives you the entire model. That means the topology and the conditional probability tables are conditional probability distributions. And all you have to do is reason with it.
We just have to fit into the model.
No, I will actually give you the numbers. Notice that basically there is no fitting here. I just gave you for the harvest. If the harvest has a particular value H, then this is the mean. You didn't even have to fit. I'm giving you everything. Now the next step, as you can see, the next step that can be done is, hey, why don't you just give me the type of the distribution? I will fit the numbers. When you do that, you're doing learning. That will separate you. Learning is separate from inference. First at least. But then we'll realize that actually learning and inference are interconnected. That's basically when, that's finally if you look at something like LDA, it's both learning and inference together. And part of what I'm trying to get you is this discussion will hopefully make it clearer as to, you'll understand LDA in a somewhat more deeper level. Okay, one other thing, which is another way of reducing the number of numbers, is this, okay, which is introduce hidden nodes, introduce intermediate nodes into the distribution. You just make them up. Okay, so for example, suppose I have a bunch of nodes and which kind of affect all these bunch of lower level nodes. So everybody here affects everybody here. Right? Then clearly, if there are, so if there are n parents here and there are m children here, then each child will require 2 power n numbers in the CPT. So you need m times 2 power n numbers. Plus, of course, the parents themselves will need numbers, that's like also 2n. Those are the prior distribution. So if I give you this network, I would need n numbers for the parents plus m times 2 power n numbers for the children. Okay. Now, suppose I look at this and say, well, really what's happening is these are all your marks and these are all your grades. And then I realize, hey, yes, ultimately your grade depends on all of your marks. Right? But then maybe your grade only depends on the average of your marks. Maybe it only depends on the sum of the marks. Yesterday was the election. Election does depend apparently on everybody's vote. But it only depends on, at the state level, there's the intermediate variables. Right? Now, if I realize that, if that is the case, then for example, suppose let's say that the sum is what winds up actually affecting all of these. Or the average of these variables is what affects all of these. Then I throw in a blue variable, a made up variable. Basically, in this case, I know what it means. I say it's average. Okay? And then I put all these guys go here, and then this guy then affects these guys. It looks like I made the network bigger, but the edges have reduced like significantly. Okay? And furthermore, now this guy still needs 2 power n numbers in the worst case, but all of these guys only need 2 numbers each. Do you see what I'm saying? Okay? So instead of n plus m times 2 power n, you need n plus 2 power n plus 2m. And you throw in big values of m and n, and you realize this is a pretty nice place to be in compared to the other one. And all you did is threw in this other thing. Now, what's interesting is this other thing also can be what raw things overall about your marks, because I'm giving the grades. Right? Okay, so this is Rao's mental state while he's looking at your marks. You have no clue what it is, right? But you may as well model it, because it at least makes your life simpler in terms of this network. Now, will you ever be able to observe Rao's mental model? Unless lobotomy is allowed, you cannot. Right? So it's a hidden value. It's a hidden variable. You won't ever expect to be able to actually observe the value of this node. And yet you went ahead and put that node in. Now, this is interesting because when I have this network, remember I was saying, instead of asking people to give the network, I might want to just learn the network from the data. Now, what would data be? What would data be? If you if you have, let's say, this is the domain, what would the data look like? It would say, on a particular case, burglary happened, earthquake didn't happen, alarm went off, John didn't call, Mary called. That was on January 1st. January 31st, burglary didn't happen, earthquake didn't happen, alarm did go off, and John and Mary both called. And so on. These are the examples that you get. This is the data. Do you understand what I'm saying? This is the data. Now, if I given the data, what you would like to do if you are into learning is just go from the data to this. So from data to model, from model to inference. This is what statistics does. However, previously what they would do is from data to a specific parametric model. Let's assume everything is normal, you just fit a normal distribution, and then after that you do normal distribution based inference. Here actually, you're trying to learn this graphical model, which basically can be thought of as combining multiple different parametric models together into a more complicated model. You see what I'm saying? Okay? So now, that's good. Now suppose it turns out, again, the data that I'm expecting will always tell me, every case it will tell me burglary, earthquake, alarm, John calls, Mary calls. But if alarm is actually a hidden variable, like Rav's mental state, you will never know what it was. So all you would know is here is a class that Rav got, this kid got 100, 100, 100, 100, 100, a C. And here is another kid who got 100, 100, 30, 30, 30, an A. And here is another kid, I'm just making up examples, Rav being just a general scenario. And so you have examples like this. Now, of course, what you want to know is what's Rav's state, right? Because in your nice network, you need to know what Rav's state is and how Rav's state depends on these marks. I'm sure you're having, sort of hypothesis that you're trying to figure out, but I didn't give it to you as part of examples. So, a learning scenario where there are hidden variables is much harder. Do you understand what I'm saying? Okay, so it's very useful to know because in LDA, when you start opening the paper and seeing it, you will see many of the variables are white and some variables are, in fact there's one node which is gray, and it turns out only the gray node is observable, and the rest of it you're making out of whole cloth. Do you see what I'm saying? Okay, now what's interesting is how do you think theories of physical world come? Okay, physical world, you get some measurements. What you measure is not directly causing each other. There may be a hidden thing which causes all of these. And this hidden thing itself is caused by these other things, which are of course hidden too. And building this theory is what we do. That's how we, survive from generation to generation, given our small place. Right? So we do this for a living, for survival of the species. Okay, the question of course is, when you have to write this algorithm, you wish that I gave you complete data. But when you have to specify the network, you are tempted to give, hidden nodes, because that makes things simpler. I want you to understand this trade-off. The interior nodes, the hidden nodes are needed so that you can reduce the number of parameters you have to learn. But now the parameters that even though there are fewer, they're harder to learn because now you'll never know. In the example, will never tell you anything about this node at all. None of the examples will tell you anything about this node. And you still need to figure out everything about this node. Yes?
So, are we assuming that we know the domain of that variable, like what kind of values it can take?
Possibly, you might, but you won't know the CPT.
But like in Rao's mental state, that example, we don't know the domain it will take the value.
Well, you can make one up, Really unhappy, somewhat unhappy, things like that. And then you can use that to figure out. Okay? Yes?
Yeah, so assuming that there's actually no hidden state in the graph, and we actually artificially add one hidden state. So, what kind of thing do we do?
That's what. The reason you would add a hidden state is you will reduce the number of parameters you have to learn. And again, some of these, as I said in the long mail I sent you before I started this class, and I'll get 2 days back, this rest of this, if it wasn't already a graduate class, it is a graduate class now onwards. Okay? Because we are actually going to try and understand something very useful, knowing fully well that I didn't take you step by step to be able to understand that whole thing. That's how graduate life works, right? I mean, you pick a paper, you try to understand it, you write lots and lots of underlining, and then you read lots and lots of papers, and then you come back and read it again, and you come back and read it again, and one day you understand. That's how real life is, okay? And this is more closer to that. So one of the connections there, essentially, the reason I said this is part of the intuitions for this depend upon things like what makes learning algorithms be feasible. If there are too many parameters to learn given the amount of data, then you are likely to overfit. I don't know if any of you know what overfit is, okay? You are likely to overfit. Whereas if you reduce the number of parameters you need to learn given the same amount of data, you are likely to not overfit. And I just reduce the number of parameters, except now I'm throwing in a hidden node. So in fact, throwing in the hidden nodes make learning more feasible. In the sense, the learned structure is likely to be more robust with respect to the sample size. And as I said, this stuff is connected to the theory of learning, which I didn't obviously do too much here. Okay. Here are some real examples which do this in your real life. Okay. So for example, light, silent light, gas. This is about I guess automobiles, right? Things like no charging. That's just an intermediate variable. It's not observable directly. Okay? I mean, to be able to observe, you have to go inside the battery and look at the chemical level. Okay? So you made the no charging, battery flat. These are essentially intermediate variables. You threw them in just so that you will reduce. So for example, battery flat is being, if you didn't have no charging and battery flat, remember, just think of graph theory. If you remove a node from a graph, the way you do it is you take all the parents of that node, connect them to all the children of that node. So there will be one edge for each parent-child combination. So to remove this, then I need to put links from here to here to all of these guys. And then I remove this, I have to do that again for those guys. So this network becomes quite busy. And people invent intermediate concepts. Okay? Just because it makes the representation simpler. Basically, again, this is a very general point we're making here. You invent it, if there aren't any intermediate representations, you invent them. Just because otherwise your life would be very hard. Okay, but then what's interesting is when there are intermediate representations, it's the intermediate representations that you use to sort of talk about your model of how the world works. So for example, right, when I wake up and I'm trying to go to the office, if a black cat comes in front of me, then it affects the alpha-beta syndrome, which then affects me to lose my balance and I fall flat on the road. This is my theory. Right? So then black cat is connected to the alpha-beta syndrome, which then makes me fall down. And then I'll make up an entire scientific career out of, looking for this alpha-beta syndrome and setting up experiments. You might say, what a silly guy you are, but I'm not particularly silly. That's what phrenologists did. They said the things that are on your head essentially predict exactly how you will, behave in the world. Okay? That's what ether theory was. We made up ether theory. There was ether everywhere. Because if you have a wave kind of undulating, there must be something in which the wave is going. And so I'll make up ether. Let's say, has anybody seen it? No, not yet. One of these days somebody will set up an experiment. And if too much time goes on and no experiment happens, then you give up and you find a different approach. And that's what Higgs boson was until the other day. You see what I'm saying? Okay? So you make these intermediate nodes, and when you do this, you make the networks more compact, but then you have to keep in mind that learning such networks would be much harder. Because exactly what is the value of this, alpha-beta syndrome I made up? it's not ever observed, and yet it is there supposedly, according to my theory. Okay, so in fact, just to kind of put things connected to at least some of you, when you have if you're given the topology of the network, okay, and all you need to do is find the CPTs, conditional probabilities, and you're given the complete data. That means you give the values, all the variables are observed in each of the training data. That's the easiest learning. It's very easy to understand. Next comes when you have intermediate variables that are hidden. When they're hidden variables, then essentially learning winds up being connected to inference. And there is an algorithm that some of you may have heard of called EM algorithm, expectation maximization algorithm. And what you wind up doing essentially is you sort of make up some distribution here, some parameters as to how these guys affect no charging, and use those parameters to infer, using the current parameters, infer what the actual value of no charging is, and then put that as, so you have incomplete training examples. You complete the training example by providing values for the missing variables. So you'll say, oh, in this example, Rav's mindset is not very happy. In this example, Rav's mindset is kind of happy. And I give all this, now I have complete examples. So I can learn the parameters. Now once I learn the parameters, I try to redo this and go in a cycle until I don't improve something. And what that something is, we'll talk about later. That's the expectation maximization. In doing that, you'll wind up doing both learning and inference together. That's what happens when you have hidden variables. Okay. The last thing is that I don't even give you the topology. I just give you the data. That is incomplete, and I don't tell you the topology. That's what is science. I have some data. I'm trying to kind of figure out some random connection. There's a great Far Side cartoon which basically shows that Einstein was sitting near a board and he was writing E equal to mc power 4, no, mc power 5, no, mc power 6, no. And then this janitor comes in and and cleans the room and says, it's all squared away now, it's all squared away. And then he realizes it must be square. Okay? The reason we find it funny is nobody tells you that the connection between E and M and C exists even. Okay? And they would certainly not tell you that is M equal to MC square or MC power K. If they tell you that, then figuring out K anybody can do. Okay? Figuring that representation that E is connected to M and C is the structure of the network. Learning the structure and learning the topology and the values. When you have incomplete data, that's fun stuff. That's the hard learning problem. And LDA does that.